So everybody can hear me? So hi, I'm a professor of condensed matter physics at Technion, and this is going to be a joint talk with Seiji Yunoki, in which we're showing you a method to push forward for quantum advantage by combining error mitigation and high-powered classical computing. I don't have the clicker. I realized only now. Thank you very much. Okay, so I think we're all aware of the fact that noise and errors constitute a huge problem for quantum computing, and they render the signal, to decay very, very rapidly as we increase the volume of the circuits we're running. And basically, for any circuit of appreciable sizes, we're not going to get any meaningful results with the error rates that we're going to have today and in any near future. So we need methods to deal with these errors. We all know about error correction, which needs a large overhead in terms of number of qubits, which also need to have very high quality. And a different method, which does not need any overhead in terms of number of qubits, but needs a large overhead in terms of the QPU time, is error mitigation. And in order to use error mitigation to get quantum advantage, you need the error mitigation method to be both unbiased, meaning that it gives you guaranteed accuracy, and it needs to be very efficient in terms of usage of QPU time. And this can basically give you high accuracy results for very large circuit volumes. Now, if you look at this plot of good qubits and QPU time, you realize that you can also combine error mitigation with error correction. And basically, this means that the fault tolerance transition is not actually a sharp transition, but it's more of a smooth crossover as you introduce more and more error correction capabilities and complement them with error mitigation. So I'm going to basically make a claim in this talk that error mitigation is going to give us quantum advantage in the very near future. And we're very close to the point where we can have quantum advantage. And I'm defining quantum advantage by the ability to execute quantum circuits with error mitigation in a time which is smaller than it would take me to simulate the same circuit on a classical computer. Now, as I said before, error mitigation requires a large overhead in terms of time. In fact, this overhead is exponential in both the circuit volume and the error rate, with some coefficient here. However, because there is this proportionality factor to the error rate, which is small, this is only a kind of a mild exponential growth, and therefore we could definitely be in a situation where, in a reasonable time scale, we can execute a circuit with error mitigation in a time scale which is shorter than the classical time it would take to execute the same circuit. Recall that the classical execution times also grows exponentially. In this talk, we're going to also show you that the timeline for achieving quantum advantage could be significantly accelerated by combining error mitigated quantum computers and high-powered classical computing. So now I want to introduce our software for performing error mitigation. Our software is called Qedma, which stands for Quantum Error Suppression and Error Mitigation. It also, Qedma in Hebrew means magic. So that's a good name for our software. And I want you to keep in mind a few very important properties of the software. First, the software gives you unbiased results. This means that your algorithm executes as if you're running on a noise-free quantum computer. The software is algorithmic agnostic, meaning it works for any circuit, any algorithm, regardless of the structure of the quantum circuit you're executing. It's also hardware agnostic in the sense that it works on a variety of different hardware platforms with completely different physical realizations of qubits. And it has a very flexible deployment. It's available either through our cloud, on on-premises devices, and it is now also available as a Qiskit function. So from a bird's eye view, how does this software works? The end user sends our system the circuit he wants to execute, the observables he wants to measure, and the accuracy he wants to obtain, and also the specific device he wants to execute the circuit on. Based on this data, we then execute circuits on the device for characterizing the errors in the device itself, in this specific device, at a particular time of the execution. Based on the results of this characterization, we perform gate optimization to basically give us higher fidelity gates. We transpile the circuit based on this characterization of errors. And then we compile the circuit into an ensemble of quantum circuits for doing error suppression and mitigation. We execute those circuits, collect the results, perform classical post-processing, and return unbiased results to the user with the errors, with the statistical errors that he requested. So if you want to quantify the benefits of using Qedma to other alternatives, I want to propose two important metrics. The first one is the circuit volume boost. And let me define that. So the circuit volume boost is the following. You set an accuracy level that you want to get. And then you can ask, what is the largest circuit that I can, in terms of volume, number of gates, that I can execute on the device without error mitigation? And what is the largest volume I can execute using Qedma on that device with some fixed overhead in time? And you can take the ratio of these volumes, and this would give you the boost factor you get from using Qedma. And of course, as the accuracy that you demand increases, this boost factor grows, and it can reach for high accuracies, boost factors of orders of hundreds and even thousands. Again, this means if the boost factor is 1,000, it means that using Qedma, you can run a circuit that's 1,000 times larger than you could run just with the device with no error mitigation and obtain this accuracy level. You can also compare Qedma to another alternative for performing unbiased error mitigation, which is PC. As I said, error mitigation always scales exponentially, but the question is, how does this exponent scales? And you can see that Qedma scales, with a much better exponent. So there is factor in the exponent, and for Qedma, this factor is 10 times almost smaller than PC. So it's a very big exponential advantage, which means, on one hand, a very big speed up. On the other hand, it gives you a much larger circuits that you can access in a reasonable time scale. So now I want to show you some demonstrations, and I want to begin. As I said, Qedma works on a variety of hardware platforms and also a wide variety of applications. So I actually want to begin with this demonstration, which is quantum chemistry VQE circuit for the ground set of the O2 molecule. And this uses 12 qubits on the order of 100 gates. And you can see here, compare the result for the energy you get when you run the circuit just on the device as is with no error mitigation, and compare this to the result you get when, the correct results for running this circuit on an ideal device. This is the black bar, and you can see the huge systematic error you get when you run the device with no error mitigation. And you can see that once you run it with Qedma, you get results which are statistically consistent with the ideal result. This is also true for other properties of this molecule, like orbital occupations, correlations. And you can see that they're all within error bars. And while the noisy results have a very big systematic error. So now I want to move on to demonstrations of large devices. And before I discuss the experiments, I want to introduce a very important quantity that quantifies the complexity of quantum circuits. And this quantity is called the active volume. So what is the active volume? So given an observable you're interested in a quantum circuit, you can ask, what is the number of CNOT gates that actually affect this observable? So this is depicted here in this kind of dark region in this brick wall circuit. Gates outside this dark region don't affect this observable. And the noise on these gates does not affect the observable either. So this tells you what is the volume that you need to error mitigate. This is the volume of, this is the number of gates that are affecting the observable. On the other hand, if you think about this in terms of classical computation, there's no need to simulate the gates which are not within this active volume. So this tells you, what is the size of the classical simulation that you actually need to run. And you can look at this active volume for a family of circuits. So I think this is quite insightful. And this is the family of circuits that we'll use for these benchmarks. And they go under the name of the Trotter-Kicked Ising model. What they are basically are layers of 2-qubit gates, ZZ rotations with some angle, and X and Z rotations with some other angles, and repeating those layers n times. We call n the number of time steps. And you can basically depict this active volume for these type of circuits for different parameters. And you can see that the active volume is very sensitive to the choice of parameters here. So for example, you can choose parameters which make the circuit exactly solvable. And then in this case, for these fine-tuned parameters, the active volume does not spread as you increase the depth, as you increase the number of time steps. This is the case for circuits called dual unitary circuits. For other sets of parameters, the circuit can be easy to simulate, but not exactly solvable. And there's very weak information propagation in the circuit and very small spread, again, of the active volume. So the yellow here indicates the region affecting the observable, and the dark purple is the region not affecting the observable. So again, you can see that there's very weak spreading here. If you choose generic parameters, then there is fast spreading of this active volume with some velocity of information propagation. And this is the generic case. This is the type of circuits that we are running when we run our benchmarks. Okay? So here are several experiments I want to discuss. The first is a one-dimensional version of this on 40 qubits, in which we measured 2-point correlators, say, for 6 steps. You can see that as you can see the shape of the active volume. As you do increase the distance between those 2 points, the active volume grows, and the signal on the noisy quantum computer decays further, while error mitigation still gives you statistically consistent results. Here are string operators at 10 steps, and you can see that as you increase the size of the string, the size of this trapezoid increases, which means that the active volume grows. The signal, again, on the noisy quantum computer decays faster, while error mitigation still gives you consistent results with the error bars. And in this one-dimensional version, we kind of push the limits. This is done on an IBM Brisbane, which is an IBM Eagle device. And we managed to go to 18 time steps with an active volume of 500. We also ran 2-dimensional versions of this on an Eagle device with 120 qubits. And again, you can see that as the number of Trotter steps or type steps increases, the difference between the noisy and the ideal results becomes larger, while error mitigation still gives you statistically consistent results. And again, you can look at these 2-point correlations and these heavyweight observables. They're all get statistically consistent results using error mitigation, and again, reaching active volumes of more than 400 gates. And very recently, we started scaling up and kind of Qedma and applying it to Heron devices. And this is like an initial experiment we ran recently, which, using the better fidelity gates on the Heron devices, you can reach much higher active volumes. So this is just an initial experiment where we ran for 13 Trotter steps and reached volumes of around 600 for these high-weight observables. Again, I want to stress that when in this circuit, the total number of gates is large. It's almost 3,000 or more than 3,000 gates, and the depth is also large. It's around 80, 80 layers. The active volume itself, you can see it here, is on the order of 600. So I want to conclude my part of the talk, and basically, based on these experimental results, I think we're very confident that with another small improvement in gate fidelity, we'll be in the regime for obtaining quantum advantage, both for ion-trapped and superconducting devices, and that using Qedma, you will be able to reach quantum advantage in the very near future. You can look at these QPU time plots. So these plots show the QPU time versus the active volume to get to a high accuracy. And you can see that once you have fidelities of 99.9%, you can be deep within this quantum advantage regime and basically start testing performance of quantum algorithms on QPUs where you cannot simulate them on classical computers. Now, I'm going to turn over the stage to Seiji, and he will basically show you how we can basically push those curves towards higher circuit volumes and accelerate the timeline for quantum advantage by combining error mitigation and higher HPCs. Okay, Seiji, the floor is yours. Thank you.
Okay. So one of the most promising applications for achieving quantum advantage is the study of quantum dynamics. Recently, in this archive paper, we explored dynamics of quantizing model on a 2D heavy hex lattice using IBM quantum computers. Our results demonstrate the emergence of the discrete time crystal even for two-dimensional clean system without introducing any randomness. A discrete time crystal is a non-equilibrium state characterized by spontaneous breaking of discrete time translational symmetry. As shown in the left panel, we started with the system in a stripe state and explored the Fouquet dynamics described by this unitary operator U, which was just introduced by Netanel, where the dz rotation angle is fixed at a particular value. And therefore, the dynamics is determined by the two parameters, theta x and theta z. And it's important to notice that when theta x is pi, the dynamics shows a trivial DTC, because the dynamics is the Fouquet dynamics is described simply by a product of Pauli operators, and therefore, the system evolves periodically between 000 and 111 state, characterizing the periodicity of two time steps, and therefore it breaks clearly the discrete translational time symmetry. So in order to mitigate errors and noise inherent in the real quantum devices, we also introduced a heuristic error mitigation method. And this method uses simply by dividing the experimental low values by those measured at theta x equals pi, where the trivial DTC is expected, as I just explained. The experimental results with this heuristic error mitigation method for 28 qubits on the IBM Torino device is represented by yellow diamond here. And those values are compared with the classically exact results obtained using state vector method. As you can see here, there is excellent agreement for time step up to 50, which is already highly significant. Even more impressively, we also performed the similar comparisons for larger systems of 133 qubits using the entire IBM Torino device. Yellow symbol again represents the experimental results with this heuristic error mitigation method, which are now compared with a classical 2D tensor network state calculations with different bond dimensions, making sure that the convergence of the classical calculations is satisfactory. Once again, we achieved that excellent agreement between experiments and the classical simulations, which is particularly significant here, considering the size of the system studied here. However, there are cases where this heuristic error mitigation method fails to produce accurate results, depending on the parameters, model parameters, and the number of layers involved in the circuit. For instance, in the region where large number of time steps are used, this agreement between experiments and the classical numerical simulations become more pronounced. And here in this experiment, we selected a particular set of parameters where this heuristic error mitigation method performs particularly poorly. And this axis is the average of magnetization across the entire 28 qubits on the IBM Torino and IBM Kawasaki. And the red curve, red symbols represent the experimental result without any error mitigations, while these green symbols represent the experimental result with these heuristic error mitigations. Notably, these green symbols deviate significantly from the ideal value, even for time steps greater than 5. However, by applying this unbiased error mitigation method, Qedma provided by Qedma, we can successfully reproduce the ideal values within statistical error indicated by these blue symbols. So how can we combine classical and quantum computations to extend the number of time steps achievable while keeping the accuracy, desired accuracy? Our approach is very simple. We divide quantum dynamics over the total evolution time t into 2 segments. The first segment of this dynamics is calculated using quantum computer, while the second segment is handled classically using HPC. Specifically, classical calculations is applied to backpropagate observable O for a time step, tau time step. And classical computing is used MPS to obtain these operators. And this allows us to measure this observable OT for the time-evolved state psi of T using quantum computer. So in this slide demonstrate hybrid classical quantum computations for quantizing model on a chain of 20 qubits using IBM Kawasaki and IBM Torino. And here, the quantum computers, the horizontal axis is the total evolution time, which is divided into classical and quantum evolution times. And these orange symbols represent the experimental result without any error mitigations. Again, these values deviate significantly from the exact values. However, when we use unmitigated error mitigations for the quantum computing provided by Qedma, the results closely matches the ideal values within statistical error, demonstrating the effectiveness of this approach. So what makes the combination of classical and quantum computations so beneficial is the significant reduction of the QPU time required to obtain the expectation value. By performing the very systematic experiment for small systems using various IBM quantum computers indicated by the storage circuits in the left, we can reasonably estimate the required QPU time as a function of active volume VA, which depends strongly on the classical evolution time. The blue curve here in the left shows the required QPU time when no classical computations is used. While this red curve here represents the required QPU time when 20 time steps of classical computations are involved. So this happens because the effective volume strongly depends on the number of circuits that are involved in the circuit. And this effective volume is effectively reduced by the contribution handled through the classical computations. To illustrate this with concrete example, let us assume that we have a total evolution time large t equal to 30. Without classical computation, the required QPU time is approximately 800 minutes. However, by incorporating the classical computations with 20 classical time steps, required QPU time reduces to just 40 minutes. So this clearly demonstrates the combining error-mitigated quantum computing with classical HPC can significantly reduce the required QPU time, and therefore this approach accelerates the timeline for achieving the quantum advantage well ahead of the FTQC era. So please stay tuned because we will be sharing more exciting results soon. Thank you.